Hello, and thank you for joining me. You're here with data science teacher Brandon, and we are going to do a computer vision project for predicting 10 different animal classes. So quite a few. This project has a special theme in the sense that I asked myself, what would I do if I didn't have a GPU? How would I train this model? That it's not huge, but it does start to take a long time when we get to this level. And typically, we'd even expand this more in a more real world situation. And so it takes a while, and GPUs really speed up. It can take a few hours with a GPU, or it can take, honestly, it took me like a week with the CPU. Kind of with timeout errors, having to restart it, load it up again, and stuff like that. So we'll go through how I saved my model at the end of each epoch, and then when it eventually timed out, eventually errored out, I was able to go to the folder where I save my models and load up my own models. So, yeah. So I'll show you how I did that today, and really how you can train, more advanced model without a GPU. It's not necessary. It does take a long time, but you only have to train it once, right? So if you train it, if you train it good the first time, okay. And it's important to get that practice training models. So let's get started. So importing our typical data science libraries, pandas, NumPy, matplotlib, and Seaborn, TensorFlow, and then we're importing confusion matrix from scalar metrics. And we're also going to use the operating system, the OS, to import some folders, files from the folders today as well. So importing that, and then what we're going to do is, so that first one, I'm gonna set the color palette to slightly different color, just so, okay. Setting my list just to show what this looks like. So if I'm going to go just inspecting the images here, so just .os.list directory. So this is going to give us all the file, in this case folders in the folder. So we get the train folder, and we have the files. Just doing the same thing. Looking at, we're going to put this into a list now. So we're going to go .os list directory, and we're going to assign this to classes. Okay, so we get this and we're connecting it this way, and we have this now set up to, we have now a list of our classes. We have to do one thing though, because the way that TensorFlow is going to do our predictions, this is actually super subtle but super important. It is going to be pulling the files from our folder in alphabetical order. If we don't have our classes here, you'll see they're not in alphabetical order. It just pulls them in whatever random order in with list directory and lister. And so with this, we just want to go sorted. Well, lowest to highest in alphabetical. And that way they will line up with, we use this classes object again later on in our code to look at our predictions. It'll be in the same ordering, so we'll be able to understand which exactly we're making mistakes on. So this right here. So what I'm going to do is we're going to look at some of our images today. Okay, so let's go, well, right now. It's always a good idea to look at images. So plt.figure, so make a figure 10 by 10. We're then going to do, and so what we're going to do in this loop, just to highlight this, we're going to do enumerate. Enumerate. This is going to give us the class, the names of these right here, and then it's also going to give us the index value. We're just going to use this as we want to put our plot in place. So and so I have this commented out. Error. So we needed that. I don't know why I had that commented out. All right, here we have it right here. Okay, and then so what we're going to do is we're going to do plt dot title or subtitle. Sorry, I apologize. So we're going to do many plots. So we want to do subtitle. So subtitle correctly, and then plt we're going to do tight underscore layout. And so it's going to take a few seconds to run. Nothing's super long. And so looking at this right here, so we can see we have shapes 200, 200, 200, 300, 300, 169. Not exactly, they're not all the same shape. Would be the point to take in. So we're going to use the image generator to set the same shape, and we're looking at it by 3. three dimensions. So red, green, blue, or red, blue, green. Sorry. We're going to set an image size. We're going to 128 by 128. And this is one of the reasons it takes a little bit longer. We're not doing super small images as we go through this. Classes, we're going to do classes right here: butterfly, cat, chicken, cow, dog, elephant, horse, sheep, spider, squirrel. And here are image sizes right here. Okay, so going into this, so let's go into our data generator. So TF dot keras processing dot image. Let's forgot that for a second. Image, and then image, capital I, image, capital D, data, capital G, generator. Okay, and we're going to do in some of the arguments to image data generator, we're going to do rotation, go width, shift, range, yeah. And then the other one, not surprisingly, height, shift, range. Okay, so width, height, and then on the bottom one down below, we want to do image data. Go through that. So we got our two image data generators. These are gonna the tool that we're gonna use to pull in our to augment our image, and then what we're gonna do is we're gonna use this to then pull our data from the file folders and really pull in the data as we go. Okay. So here we're gonna do here in the data generator, we're gonna go flow with the data gen dot underscore train. We're gonna flow from and the director. Okay, and we can do here we can flow from directory. Okay. So here we're going to do target size, not image size, target size. Target size. We're going to do batch size. We're going to do shuffle. We're going to do color mode. Class underscore mode. Okay. We're going through all of those. So we're just getting our flow from directory. So this is setting up our augmenter that then is going to, this function, so then we're going to pull in the data from the directory and then augment it on the fly. And then we'll be able to augment our images every epoch. Okay, so this one, make sure everything's good. Okay, we found 10 classes and 10 classes. Okay. So here, let's write the whole loop for this. So now we're going to look at our image data generator. Okay, so what we're going to do is we're going to go for or image label in, I'm going to call it probably image data generator, yeah, generator training. Okay, we're going to go plt dot im show on the inside of our, in the first line of our for loop. So tf dot arg max. So this is going to, on the row, on the axis 1, so across the row, is going to pull out which position is the highest prediction, and that's going to be our target rate. So that's how we needed TensorFlow needs in that format to do linear algebra on our targets. So let's run this, and then just to highlight here, we're going to use or not exactly while similar to while we're going to use a count thing, and then once it's greater than or equal, once it's equal to 5, so once it hits 5, we're going to stop this counter. So we're just looking at 5 inches. You can see here little shift up and down and stuff like that. So this is makes our model, it helps regularization, I guess you could say, for computer vision, but it helps make it not, I guess you could say, overfit to where the position is of an object in the picture. So this is always over here versus now it can be anywhere. So we can actually learn the eyes can be really anywhere. We can learn the different features, the chin, the nose, everything, the ears, sorts of things can be anywhere, and we're finding the images, really the shapes, the patterns versus just the patterns are in this specific shape. Okay, so it's really important. It allows you to train your model off of a lot less images. Okay, so really helpful. Okay. So that's our image data generator. And just also noticing here, the reason that we did this in a loop is because we are not able to just access the data like we would even if it were rows. It's not accessible like a pandas data frame. We have to call it essentially. We have to use it, and then once we pull in, that's going to be our batch size. We're pulling in a certain number, and then we're looking at one every batch. We're looking at the first image of every batch, and we're doing that 5 times. Okay. And so going through that. Okay, so going there, and then what we're going to do, we're going to get into our architecture. So I always like to have my hyperparameters up above at the start. So for our architecture, we're going to do convolutional filter 64, 4x4 kernel, 28 convolutional filters, 4x4 filter, or kernel, sorry, pool size of 5x5 all the time. And for our activation function for our convolutional network, we're going to do a tan-inch, okay? Hyperbolic tangents. Okay? And so the idea here is we're going to use this twice, and we're going to use this twice. We're going to use this, then we're going to do a pool, a dropout, use this twice, or I guess both of these, use this size twice, max pooling, drop it again. And you truly can do this many times. To do this on a CPU, I didn't want to do any bigger than that, but I have many times done 3 or 4 groups of the convolutional layers. So the 2 sub layers, the 2 convolutional layers, and then the max pooling and then dropout. Dropouts are just so important to prevent overfitting. Okay, so then here we're going to do something special. We're not using the standard dense layer. We're using a recurrent layer instead of the dense layer that has been kind of traditionally proven to work really well. And so here for the dense layer, my favorite one for dense layer is the ALU. We typically use that. And then our output activation is we're doing multi-activation, we're going to do nn.softmaxes. Our loss is going to be categorical loss. Okay. Categorical cross entropy. Okay. And then I guess the special thing that we're going to do today is so that we can save our model and train it on a CPU instead of a GPU, where we might not be able to train it for the full 300 epochs in one sitting. We might need our computer for other things. We're going to get this from the keras library. We're going to go keras callbacks. And we're going to go model, capital M, model, capital C check. And we're going to get our file path to file folder where we want to save our model. We're going to give it, so here we're saying, tell us what the epochs are, tell us what the validation accuracies is. Okay? And we're going to do save weights only, and we're going to set it to false. Okay, so to false. Okay, and so we're going to say the model will be able to load up again. So let's run this to make sure it works. Okay. So then let's define our model, our layers. We're just going to do the layers. This is level 6 project, but already in tf.keras.layers. Every time is a little bit much. Okay, so just going to do the I guess the action part of the layer. Okay, so convolution right here. So cov to D followed by another cov to D and capital C. I think this should be capital to D. And then we're going to do max pooling to D. Okay. And then we're going to do capital D dropouts. Okay. Very important dropout. Okay. And then we're going to do this again. So cov to D followed by another cov to d, our pooling, so max pooling, to d. Okay. And then we want to flatten our layers. And then follow by dropout. Can't forget that dropout's just always so important. Our dropout layer right here, and then what we're going to do is follow this by a dense layer. And we're going to follow this by a reshape. Layer. Here we're going to do reshape. We're going to do simple. It was left in there. I guess I just put the none in front of that. I apologize. But simple RNN. You can use the LSTM. Really, any layer that you really choose to. I like the simple RNN. It works well. It's a little bit faster and it works well. It's a good starting one. And to just because it's a little bit faster, I wanted to try and make this as easy as possible. And it still took me a couple weeks to train this model just in the background. So dropouts, and after this, doing a dropout layer, another dense layer, and then a dense layer to finish this off. We're then going to compile our model right here. I'm going to do a little bit of compile. Loss is equal to our LS up above, our categorical cross entropy. Our optimizer is equal to our optimizer from up above, and we want to get the metrics. Metrics within E. Let's run this, make sure everything is run correctly, and no errors. Okay. So here what I'm going to do is, so you can see right here, the green right here that I have right here is where it would fit the model normally. To show you kind of what I did the second time, so this is what you normally train the model and stuff. And then right here I have where you would save the model after training, like plot the history before and then, but just save the model and do this. This is where I would, after I'd look at it, but our checkpoint is going to save this every time as well. So if I decided that I wanted to save it again, I call model. It's going to, sorry, I apologize. It's going to save on the end of it, a checkpoint anyways. If I wanted to access the model, then I go keras, tf.keras, dot models dot load underscore model, and then load up the model. I load up my model right here. Yep. It's still going to take a long time even to do a prediction, so I won't predict this. It does take 10 minutes to do the test set, and this is like basically an hour. A little bit more than an hour and 10 minutes. It takes a little bit long. It takes quite long, so it's not really worth doing and stuff like that. Just looking at the predictions here, you're going to test out our predictions here. You see I'm doing the same thing, very similar to the loop up above. The one difference is I'm doing my model.predict on my image, right? So as I'm getting it from the train generator, and I'm getting it from the test generator right after, I'm going to get the predictions. So what I'm going to do here is I'm going to do confusion underscore matrix. And we have tf.arg max. So I guess I should actually start before I keep going right here. I'm not going to train the model today. I just did. I didn't think you want to watch me for a couple of weeks. So I'm not training the model today, just showing you the loading up the model and showing you how I trained right here with the train, looking at the history. We don't have access to the history anymore. So because we've done it over many times, there is ways just to do that and stuff like that, but it's not necessarily built in where we could save our history or output of our model. It would be nice to have. It certainly would, but we just, again, we don't always have access to that. Which is fine, not the end of the world and stuff like that. We can keep training until we notice really no more improvement. Okay? So in our confusion matrix, we're going to give the two tf.arg maps. So we're going to get the highest argument of the row And when it comes into the generator, it's going to be the row. So we're giving our true values and our predicted values, getting the row across the values, and this is what the row looks like in the true sets. Right? So we're going to highest one here. Hopefully, your prediction is the same. Column has the highest value in here, and that'll be your prediction. We're going to put this. We're going to get our confusion matrix right there. We're going to then put this into a data frame. We're going to put our index equal to classes from up above, and our columns equal to basically a list comprehension that's going to quickly add pred to the value. So nothing really super special. We're going to put this then into a heat map, and then we're going to plot dot title. And this looks pretty good. So we've got really good prediction. It's almost easier to get a decent computer vision model. It's pretty easy to get one that works at least pretty well. I feel that pictures are literally numbers, right? We're seeing 3 channels of 3 different colors. So you're seeing me. That's beautiful pink background that I have today. It's 3 channels of colors, right? And you're seeing that, and that's so it really just pictures are already numbers, right? So it fits very easy. Unlike NLP, is a little bit trickier to get a good model that works well. Pictures are pretty easy to get started with, and so we have a good train model. Doing the same thing for the test right here and showing we got really good for the test as well. And what's typically done though is that we did 2 blocks of the convolutional layers. Typically 3, maybe 4, 3, and then 1 more, something like that. There's a few different kind of techniques, but 3 or 4, I would say, is for really good prediction stuff. We should be able to get about a 9.5 sort of thing with that model. Even on 10. So this is good. So you can see here, we do notice though that we didn't have any predictions for the squirrel. So we didn't get any squirrel predictions like that. It was very undersampled, underrepresented data set. We made a few in total and stuff like that. So I should have maybe not used the squirrel one because there really is just a very small amount of images. So we didn't even see, we got maybe just a couple, I think, on the training set. 1 prediction on the squirrel. Just again, it was really underrepresented. So it's probably incorrect to use such an underrepresented target. But again, trying to see what we can do and stuff. Squirrels are small. Hard to get pictures of them, I guess. And going through that. So thank you very much for joining me today. The model can be loaded up from the website, from the page, the one at the top, can be loaded up using what I showed you there. The images are there as well. Have a great day. Thank you so much for joining me today.